Hi everyone, so in this video we'll introduce a basic example just to establish the notation of the computational graph and explain how is it different from the notation of the neural networks that we use. And the point is that just to avoid the confusion, because we draw both as graphs, right? But remember that a node in the computational graph or a vertex in the computational graph corresponds to one operation, right? So for example, I could have a neural network with ni nodes here, right? And then in the second layer, I have one neuron in the second layer, and that neuron is connected to multiple nodes in the first layer. Now, this neuron, let's say W2 to WNI, right? Now, this neuron, to compute its value, right, we have weight multiplications from neuron number 2 to neuron number ni. This is one operation in the computational graph. And then we have a bias, right? So here we have W2, X2 plus W, NI, XI, right? Plus B1. And all this, and then let's say I have ReLU, maximum all this and 0. So the weight multiplication, this constructs one vertex in the computational graph. The bias, another vertex afterwards in the computational graph. The max with 0, a third vertex in the computational graph, right? And they are in different layers, right? So I have the x1 to the x2 to xni, right? So this is xni in the computational graph, right? And then I have one node corresponding to W2x2 plus up to WNI xni, and then that new vertex containing this value here from the W2x, this value here, right? Plus B1, that's another vertex in the computational graph, and then a third layer, a third vertex in a third layer applying the ReLU function. Right? So one layer in the neural network here in that example corresponds to 3 layers in the computational graph, just to avoid the confusion when we use the notation of the computational graph, which we will mainly use for discussion of backpropagation. Now here in that basic example, we have a computational graph. The inputs are ni inputs, and the output is just one scalar output. And just for like to establish rigor in the notation, so first we set the inputs to the neural network as the inputs of the computational graph, and then for every I, so there are only ni inputs. Now all the other vertices ni plus 1 to n are not inputs. For I equal ni plus 1 to n, we set ai as the set of nodes uj that are parents of ui in the computational graph. So a parent here, for example, u1 is a parent of u10. So a vertex in the computational graph corresponds to an operation. A parent is an operand of that operation. So that operation is computed as a function of its operands, as a function of its parents. And then ui is computed as a function of the parents of I. Now let's go to, so this is the forward propagation step. Let's see the backward propagation step in that simple example. First, we say that we run forward propagation, right? Why are we doing this? To obtain the activations. Why are we running forward propagation to obtain activations? Because in backward propagation, we compute the derivatives or the gradients, right? Now these gradients have different values depending on the region of the nonlinear activation function. For example, this is a ReLU activation, right? If you're in the active part, the gradient has a certain function, has a certain expression. If you are in the non-active region, the gradient has another expression. So you cannot even compute the backward propagation computational graph without knowing the activation region of the nonlinear activations. Now the backpropagation computational graph is a graph with the same number of vertices as the forward propagation graph. There is a vertex corresponding to every vertex. There is a vertex corresponding to there is an edge corresponding to every edge, so it has the same topology. But now every vertex in the backpropagation graph has the value of the derivative of the output with respect to the corresponding vertex in the forward propagation graph. For example, this, the top of the computational graph here, has partial un, partial un. Because un is the vertex in the corresponding forward propagation graph. This vertex here has partial un minus 1. Because un minus 1 is the corresponding vertex in the forward propagation graph, and so on. Now, to compute the value of every vertex, we do the following. So first we initialize what we call grad table, right, which is a table of gradients. And grad table of u of n equals 1 because partial un equals 1. And then for the rest, we compute grad table for every intermediate node uj as the following. We find all the nodes such that j is a parent of them in the forward propagation graph. So for example, here I am at u1. I find all the nodes that u1 is a parent of them in the forward propagation graph. So here u1 is a parent of u10. If I am at this point here, u2, I find all the vertices such that u2 is a parent of them in the forward propagation graph. u2 is a parent of u10 in the forward propagation graph and is a parent of u11 in the forward propagation graph in that example. And then I find the value of grad table of u of these of ui. So here this is partial un, partial u10. That's the value of grad table of u10 times partial ui, partial uj, which is partial u10, partial u2. So imagine every edge, right, that includes the nonlinear activation, such as the ReLoop, has the value of the immediate partial derivative between the child and the parent corresponding to that edge in the forward propagation graph. And then as I go backward in the backpropagation graph, I have the value of grad table times the value of the derivative along this edge. And then I sum, so here to compute grad table of u2, which is partial un, partial u2, I do that for u11 and I do that for u10, and then I add the corresponding values. And then at the end we return the values obtained for the input nodes, which are ni vertices in our basic example. Now next time we will discuss the problem of computational complexity, and we'll see that that basic example strikes an extreme point in the trade-off between memory and computation by being extremely computationally efficient and at the cost of extreme memory storage. Thank you.